Now we move towards our next presenter, Engineer Kashif Iqbal from UET Taxila. Kashif, are you with us? Jawad, you can unshare your screen, please. Welcome, Kashif. Please share your screen. Walaikum assalam. Kashif will be talking about energy loss in emergent, rigid, and flexible vegetation. Kashif, again, please try to limit your presentation within 10 minutes.
Okay,
Go
sir.
ahead, please.
Will you hear my voice, sir?
Yeah, I am getting your voice clear.
Bismillah ar-Rahman ar-Rahim.
Yes, your screen is also visible. Your screen is also visible. Please change it to the presentation mode. If possible, change it to presentation mode. Otherwise, go ahead, please.
ठीक है, sir. Assalamu alaikum.
Kashif, please start.
Sir, are you hearing and seeing my presentation? क्या इधर कैसे शेयर करूं?
Nabil, please mute your mic.
Sir, kindly share my slides.
Yes, we can share. We have your slide. We can share it from here.
Yes, sir. My name is Kashif Iqbal, and I am a yes, sir. So my name is Kashif Iqbal, and I am a research. I have done my MSc research from UT Taxila Civil Engineering Department. My research supervisor is Dr. Usman Ghani. And the topic which I have to discuss here is that energy loss in emergent, rigid, and flexible vegetation. And the paper ID which is given by Center of Excellence is 104. The content of my presentation is introduction, experimental description, vegetation condition, results and discussions, conclusion, and references. Next. Next, please, sir. Introduction. Flow dynamics can be highly complicated and occasionally cross erodible limits during the interaction between flow and vegetation in floodplains. Since floodplains management and river restoration have become more significant over the past several decades, numerous researches have been conducted to better understand the effect of both rigid and flexible vegetation on flow hydraulics. The corridors such as known as riparian corridors or areas had been used as flood protection strategy, and also such protections have been thoroughly investigated. Most researchers consider the placement of vegetation. Number one is that perpendicular to a direction of flow, and they have found the energy reduction plot in staggered patterns such that, but in line patterns are not studied so far. So in the present study, the experiments were carried out in the laboratory, and the amount of energy loss was measured in case of emerging rigid and flexible vegetation with varying vegetation thickness, its density, and upstream fraud number. The results of this study could be used to provide different types of vegetation to protect floods on riverbanks and flood-prone areas. Next. Next, please. Next. Next, please. Experimental descriptions.
Kashif, which slide you want?
Sir, experimental descriptions. Yes, it's okay now. The experiments were performed in the hydraulics laboratory of Civil Engineering Department at the University of Engineering and Technology, Taxila. The flow, which is shown in figure, that is 10 meter long, 0.45 meter deep, and 0.31 meter wide. Rectangular channel used during the experimentation. The channel had a flat bottom with a metallic bed, and a flat bottom with a metallic bed, while the sides of the channel were made of perspex. The water level was measured using a point gauge along the middle of the channel. A full width vegetation model was placed in the channel at a distance of 4 meters from the upstream inlet. Two vegetation cases, a low pervious vegetation, that is the value of porosity will be 0.90, and a high pervious vegetation were used. And basically the flow was subcritical in both rigid and flexible cases. The flow numbers of 0.38, 0.54 and 0.56 were chosen to make sure that the vegetation model would be realistic at very relatively low values. Next, sir. Another is basically the vegetation condition. If we move to another slide, the rigid and flexible vegetation were modeled at 0.7 centimeter, which is basically 7 mm diameter, wooden stick and glue sticks in a uniform pattern. Uniform arrangement of vegetation was used, and the height of vegetation elements, both rigid and flexible, were 28 centimeter. As we can see from the two-dimensional views, the arrangement are linear in line pattern, we can say it, because the study of staggered patterns have been studied so far. And the second diagram is basically the flexible vegetation, which is used, which tilts in the downslope direction to dissipate the flow energy. And the third one is the rigid vegetation, which is used. Basically, the rigid vegetation, it implicates in actual reference, if we take it, is the eucalyptus tree sophyda, which is known as sophyda, used in Punjab, and it requires more water. Next is the different geometric and flow parameters used in this research work. The vegetation models with two different values of porosity were used, as I have mentioned earlier, to determine the first column represents the vegetation type, the other is the flow parameters, the PR represents the porosity, and WV represents the width of vegetation. Then we can decide from this that either the vegetation is low pervious or high pervious. Next, results and discussion. If we come to the next slide, results and discussion. Effect of vegetation, porosity, and fraud number on backwater rise. What will be the effect if we come close the vegetation, spacing of the vegetation, and increasing fraud number? What will be the effect? The slope of water surface inside the vegetation patch and depth of flow at upstream side of vegetation patch increases by decreasing the porosity of rigid and flexible vegetation. It can be observed that the backwater lies is lower for higher porous condition of vegetation patch as compared to low porous condition for a given fraud number compared to high porous arrangement to the low porous, and shows high flow resistance, which cause a high backwater rise. The initial flow condition was varied by changing fraud number that is 0.38, 0.454, and 0.56 in the absence of vegetation model. The water level at upstream side of vegetation increased by placing the rigid vegetation model in the channel, and the water surface slope inside the vegetation became larger. Hence, by increasing the initial crowd number, the backwater curve was slightly increased for rigid vegetation. Next, please. But in case of flexible vegetation, sir, if we come to the next slide, in case of flexible vegetation, the water level, it is oppositely a replica, opposite to the rigid vegetation. The water level at upstream side decreases by increasing the initial crowd number, and hence backwater curve slightly decreasing as the flexible vegetation tilts in the downward. We can see from the graph clearly by increasing the crowd number, the vegetation, the backwater rise is increasing in the first graph, which represents the rigid vegetation. With another graph, we can see that the backwater rise decreasing by increasing the initial crowd number, because in flexible vegetation it tilts in the downslope direction, so more water will go from the upstream to the downstream rather than to backwater there. Next, please. Another term used, another phenomena which exists in the downstream of the vegetation is basically the energy dissipation, and the energy of water per unit volume at a section measured with reference to a channel bed is known as specific energy. Specific energy is expressed in this, where E is the specific energy, Y represents in this formula the depth of water, V represents the fluid velocity, and basically alpha is the energy coefficient used, which is has value of unity. So I have not mentioned in this equation that value. The total energy loss delta E through the vegetation patch is E1, delta is equal to E1 minus E2 divided by E1, which represent the E1 is the upstream energy loss at upstream of the vegetation, E2 is the energy loss at the downstream of the vegetation. The above equation was utilized to determine the energy loss through vegetation patch, and the final results of energy dissipation is basically for low pervious vegetation, the maximum energy reduction due to rigid vegetation reached to 58.30%, whereas for flexible vegetation it reached to 40.85%. And if we go to the high pervious vegetation, the porosity of value is generally taken as 0.97. The energy sir.
I request you to please go to your conclusions. You are already over time.
Sir, only 1 minute. Now, energy loss for rigid vegetation is 39.32%, and that for flexible it reaches 28. Figure both shows the energy dissipations in rigid and flexible vegetation. From the one which shows the backward, the dissipation increases with increasing the fraud number, and the other it decreases with increasing the fraud number. Next is the conclusion. Against varying vegetation thickness, decrease in the porosity of vegetation increases the backwater curve on the upstream side of vegetation due to high vegetation resistance. And the principal conclusion is basically on downstream side, energy was lost due to resistance offered to the flow. The energy loss in rigid vegetation is 17% more than that of flexible vegetation in low porous arrangements. So we can finally conclude that if you use rigid vegetation in riparian areas of the floodplains where the flood inundation is very high, then it can dissipate more energy as compared to flexible vegetation like bamboos, grass, and anything else. References. Next is the references. And at the end, thank you. Any question?
Thank you very much, Kashif. Question may be taken